of the primary colors, red, green, and blue. And we have there, by the way, red, green, and blue are also primary colors of light. So create other colors by forming linear combinations of R, G, and B using coefficients between 0, 1, inclusive. So we have here thus each color vector C is expressible as a linear combination of the form C is equal to K1R plus K2G plus K3B, where K1 is multiplied here in 100, and then K2 is multiplied with 010, and K3 is multiplied to 001, where 0 is less than or equal to Ki, less than or equal to 1. So your red class is represented by this vector 100, which is there, and then G is 010, and then your blue is 001. Okay, so if your K2 there class and your K3 are zeros, then you can form a color red because, for example, your K1 there is a Ki there, a K1 is equal to 1. That's it, it's a color red that will appear. Okay, next. You have this color combinations here. Okay, now actually this vectors here class will form the span, it will span R3. So by the way, that is our next topic. The set the following vectors v1 to vm, a vector space V spans V if for all W element in V. Okay, so for all W class, this is vertex, a vector element in V. There exists lambda I element of real numbers such that we can express all the elements of the V there, like W here, is equal to the summation of this gamma I I from 1 to M, where your VIs are this one, V1 to VM, where they are elements of your S. Okay? And then your lambda I are element in the set of real numbers. So it's equal to this one, lambda 1 V1 plus lambda 2 V2, and so on to lambda M VM. We denote it by V spans S or span this one, V1 to VM. Or your set S there is a spanning set of V. So we have this one. Consider S be equal to 10 and then 01 for all W element in which is equal to x1, x2, where this x1, x2 are element in R2. So R2 means the set here are or set of ordered pairs. Okay, so we have this one W is equal to our x1, x2 class, we can express it like this. We multiply x1 with the first, and then the second we multiply it with x2. Now, if you multiply it here, this becomes x1 0 plus 0 x2. Then when you add it, it's x1 x2. So we will do that every time we have two vectors in our set S. That the product here, when you multiply there with x with this, now your x1 here is your lambda 1 and your x2 is your lambda 2 from the previous slides. Okay, now this is easy if that is 1001. So what about if it's not that set? So for example, we have vector. What if we have this one 1211? So if you have there 1211, you cannot multiply this by x1 here in your 12 plus x2 times 1 there, because when you do that, it will not result to x1 x2, correct? So what are we going to do there is we find, we use another letters or variables. We have a and b there, and we multiply it in the 1 2 plus b there is 1 1. You multiply b there in 1 1. Now, what if class 1 of the numbers there is 1 0? For example, this one is 1 0. Yeah, for example, this is 1 0 and 1 1. So if that is 1 0 class, you can use their x1 because when you multiply x1 there, wait, we cannot use x1 also because you will multiply another variable here. It's b times 1 1. Then when you add the first component, it is not x1 yet, right? So, okay, we cannot use that. So even if this is 1 0 class partner with another number, still you have to use a and b. Okay? So multiply this one with a, and then the second one is b, and then you will say like, can we use another letter? Yes, you can use c and d combination or s and t. It's up to you. Okay. Now we have this, multiply a here. We have a as the first coordinate, then the second coordinate is 2a. Here the first coordinate is b, and then b is also the second coordinate because we multiply that with 1 1. Now add the first components. The first components is a plus b. The second components, you add it, it's 2a plus b. Now this a plus b here must be equal to your x sub 1, and then your 2ab here must be equal to a plus b must be equal to x sub 2. So that's it. We can form this. A plus b is equal to x1, and then 2a plus b is equal to x2. Now class, since your x1 and x2 there are arbitrary elements in the set in R2, and also your a and b are arbitrary elements here. Okay, so it is difficult for you to find a value of a and b there. Okay, so what are we going to do is just get um, the constant. Just get the constant here, class at this side, the left side, and then get its determinant. Okay, so if the determinant is not equal to 0, your S will span R2. So this one, the determinant is 1 times 1 minus 2 times 1. The answer is negative 1. So the answer is not 0. Therefore, S spans R2. Okay, so we have a result later that if it's equal to 0, it will not span R2. If the determinant is not equal to 0, it will span R2. Now, this kind of solution is only applicable to square matrices. Okay? This is only applicable to square matrices. You use determinant. Next, we have this one. 1 1 1 1 0 2 does not span R3. So here, class, the matrix that we can form is a 3 by 2 because you have here 1 1 1 and 1 0 2. Now in this solution, it will span R3. Your S will span R3 if there's an alpha and beta that you can multiply the two there, 1 1 1, and then b times a beta times 1 0 2 is equal to, it should be equal to x1 x2 x3. Okay, now class, in this example, we use alpha and beta here. And then the previous one, we use a and b. Again, it's up to you what variable you want to use. Okay, we can use any variable we wanted to. Okay, next we have this one. First, a plus b is equal to x sub 1. Your alpha, it's alpha. Alpha is equal to x sub 2. Here, your alpha plus 2 beta is equal to x3. Now, if you solve that, um, we have to make this 0, right? Your alpha is 0, and this one be 0 here. So we have to subtract this. Equation 1 minus equation 2, we have alpha minus alpha is 0 alpha minus beta here, and then x2 minus x1, and we have the second row. Okay? Next, if you minus the first, no. If you minus the second here in the third equation, this becomes 0 alpha, correct? 0 alpha plus 2 beta, and then, we add it. We add the second here. We add the second here, so we have alpha added here. We have 2 alpha plus 2 beta is equal to x3 plus x2, correct? And then next is this one here. This is alpha plus beta is equal to x1. You multiply them with 2. So 2 alpha plus 2 beta is equal to 2x1. So they are now the same with the lower one. Again, the lower one becomes 2 alpha plus 2 beta. And here we have 2 alpha plus 2 beta equals 2x sub 1. Now subtract it there in the third um, row. We have there 0 alpha now plus 0 beta. And we have x sub 3 plus x sub 2 minus your 2x sub 1. Okay. So it's consistent for all x sub 1, x sub 2, x sub 3. So this system may have no solution or may have solutions depending on your x1, x2, x3. Now if you choose there, so this is arbitrary class choosing. We choose arbitrary x1, x2, x3, which is equal to 1, 1, 2. So this system becomes inconsistent. Therefore, 1, 1, 2 is not a linear combination of vectors in S. And now, class, to show that it will span or will not span R3, we use its rank. Okay? Now, why are we using rank here? Okay, if the matrix class that it will form is not a square matrix, you have to use the rank. We have what do you call this? A theorem after this. Okay, so that is 1, 1, 1, 0, 1, 2. The rank is 2. Okay, so what to do, class? You arrange the vectors here. The first vector, you arrange that the first column, and then the 102 is in the second column. If you convert that into matrices. And actually, class, it's the numbers here. 1 1 here in your alpha plus beta, 1 1, 1 in the alpha, 0 in the beta, so 1 0, and then 1 2. They are just the constant here in this equation. Okay, so the same with what we did here. Just get the constants here. It's 1 2 1 1. So that's the arrangement of your vectors. If you have your vector 1, your v1 1 2, you arrange that in the first column, and then your second v2 here vector, you had to arrange it in the second column. They're just the same arrangement. So now, how to get the rank? So it's easier to get the rank if what to do here. You make this 0, right? You make this 0 here, and you make this 1 here. Okay, now we solve the rank. You should have their leading ones. 1 1 1 0 1 2. If you have your MATLAB, it's easier to see. If you have their A is equal to 1 1 semicolon 1 0 semicolon, and then 1 2. This is your A. Now if you want to get the rank, it's easier if you have an RREF of your A. This is the reduced raw echelon form of your A. is equal to this. So as you can see, you have there two leading ones only, one here. So the rank is 2. Now class, it is less than 3. So S does not span R3. So we have that result later, that if the rank is less than 3, the 3 there class is actually the number of the components here in your vertex, in your vector, sorry, the number of um, coordinates here in your vector. You have your three numbers, right? First coordinate, second, and third coordinate, and it's not equal to 3. So it's only 2, so it will not span R3. So we have a result later that if the rank is equal to 3, it will span the R3 there. And we have this. Now you see it already. Um, R, if the rank of A is equal to N, then it will span Rn. Next, if the rank of A is less than N, this vector set of vectors from V1 to Vm does not span Rn. So that's it. Um, it's equal to 2 and not 3 there, therefore it will not span your Rn. And we have this note. N is the number of the coordinates of your vectors from V1 to Vm in Rn. Okay? Should be the number of coordinates of vectors. Next, special case class. If you have a square matrix, M is equal to N. As I have told you, do not use rank here. We use here determinants. Okay? So, if the determinant is not equal to 0, then it will span Rn. If the determinant is 0, then the set of vectors does not span Rn if it's equal to 0. So we can check it there. It will span if not equal to 0. And we have this example. Okay, here the determinant is not equal to 0. So S spans R2. And then this one, its rank is 2. Again, it will not span R3. Okay? So you have to remember the properties for if it will span or not. Again, it will span if the determinant is not equal to 0. And the last is if the rank of A is equal to N. So there's a property that it will not be equal and equal to N. Okay, now next we have these two sets, the linear dependent set and the linear independent set. So for the linear independent set, we start here because this is easier to explain. You have there, if you have this summation there, gamma I, I from 1 to m, it's equal to 0. So we only get this value that the lambda there, the lambdas are all equal to 0. Lambda 1 to lambda m are all equal to 0. Now it is linear dependent set if your lambda there are not all 0. What that is what it means here, because it will satisfy here. There exists lambda 1 to lambda m element of the real numbers such that the squared of the lambdas is not equal to 0. So if you add them, it's not equal to 0. So now, if one of them is not 0, then it will satisfy this, right? Because if all of them here will be 0, then this one becomes 0, and it will contradict to this assumption. Okay, so again, all your lambdas here should not be equal to 0, such that the summation is equal to 0. So they are the same. The summation of lambda I vi is equal to 0, but in linear independent set, all the lambda there are zeros, but here in the linear dependent set, all of your lambdas here must not be equal to zero. So if there exist two numbers, for example, that are non-zero, so it is linear dependent set, and that's it. So this is the graph representing the linear dependent also here, and then this one is linearly independent. This two, A and B, are for the linearly dependent, and the graph here, linearly independent. The graph, the vectors here. Okay, linear independence or linear dependence of V1, V2, Vm is determined by whether there exist non-trivial solutions of the system lambda 1 V1 plus lambda 2 V2 until lambda m Vm is equal to 0, where your lambda 1 to lambda m element in R are the unknowns. So if the system has trivial solution, all of them are equal to 0, then that's linearly independent. Next, if the system non-trivial solutions class means not all zeros in your lambdas, okay, in your lambda 1 to lambda m. And that is what you call linearly dependent. So let A be equal to this one matrix, and then let determine the rank of A. Oh, we have also the rank here class for linearly dependent or independent. If the rank of A here is equal to M, that is they are what you call linearly independent. If the rank of A here is less than your M here, then that is the vectors are linearly dependent. Okay, so you have to take note on this one. Next is okay. Class for square matrices, we use determinant there. If the determinant is not equal to 0, it is linearly independent. And then determinant of A is equal to 0, they are linearly dependent. Okay, that's it. Next. So determine whether the V1, V2, V3 are linearly dependent. If you arrange them, again, for the V1, you arrange that in the first column, V2 second column, and then the V3 numbers are in the third column. So you have that. Okay. Next. This is what it means, class, because there's a T there, so you have to write it's transposed. So instead of writing this in the first row, you write it in the first column. Okay? That is why there's a T there. Next, we have determinant of A. The determinant of A here is equal to 5. Therefore, linearly independent. So class, we do not have lots of time to solve for the determinant of this, but I know you know how already, right? Get to there, then delete this row and this column. You have there 2 1 1 4. Get the determinant of that. The next minus 3, because this is the next number in the row, right? So minus 3, then remove this, remove this. You have there 1 1 2 4. Then plus 1 times the matrix 1 2 2 1. Correct? And then you can get there 5. Now to get that easily, we can use our MATLAB to do that. Okay, we have there 2, 2, 3, 1, semicolon, then 1, 2, 1, and then we have 2, 1, 4. So we have that matrix. Then just type there class det of A. That's the determinant of A, and you can get there 5. Okay? So it's easier for you to verify if the answers here are correct. So that's determinant of A is equal to 5. It's not 0, so it's linearly independent. We have this one, right? If not 0, linearly independent. Okay, again, class, you get the determinant if that is a square matrix because this one is a 3 by 3 matrix. Next, we have this one, another 3 by 3 matrix that we can form here. 1, 2, 3, 4, 5, 6, and then 7, 8, 9. Plus, you can go directly with this arrangement. No need for you to write this during test. Okay? So that it will not take time for you to just write the A matrix and then solve its determinant. By the way, there is other way of solving the determinant here, right? Do you remember it? You can make the other two numbers here be 0 and then get the determinant using the first column. Okay, you can apply elementary row operations here. For 2 and 3, you make this 0 and then that's it. You can just compute one part of the determinant and then you can get it correctly. Okay, next, this one, it says that the determinant of A here is 0, so linearly dependent. Okay, the other one, the determinant is not 0, linearly independent. So let's try this. If it's really 0, so another A here. By the way, class, if you write another A here in the system, um, it will get the newest A value. So the previous matrix A there, the system here will not accept that anymore. So since I define here another A, that is the A if you mention something like this. Determinant of A again, it's here 0. So it will neglect this previous A class, okay? So if you mention A here again, it will use this matrix. It will not use the other A there. But if you want to use this again, just copy this one and then type it here, then click enter. Okay. If you want to reuse a matrix. Okay, next we have that 0. Next, how about this? Now this is now a 4 by 3 matrix. So we cannot use now the determinant anymore. So what are we going to do is to get the rank here. Okay. So what he did is we will now perform the elementary row operations because we have to make the zeros here. The 1, 2, 3. Make that zeros. So we multiply -1 in the row 1. This is 1 already, so it's okay. Multiply -1 in the row 1 and add row 2 to get the new row 2. So just minus it here. We have 0, here 1, and then 2 minus 1, 1. So it's 0, 1, 1 in the next number. Okay, it's here 0, 1, 1. Next, you multiply -2 in the row 1, all of that, and then add it here in your R3 to get the new R3. So -2 here, this becomes 0, -2, so that becomes -4, plus 3, it's -1. Then multiply this with -2. -2 plus 1 here, it's also -1. So 0, -1, -1 is 0, 3. So I will not solve that all again. So if you apply this in the row 4, you can get 0, -5, -5. Now, make these two numbers here be zeros, the -1, -5, and perform this elementary row operations, and you can get this. Now, what happens is the row 3 and row 4 becomes 0. So what is the rank here? The rank here is 2. So the rank of A here is 2 and not equal to 3, which is equal to your M. And therefore, your V1, V2, V3 are linearly dependent. Okay? Your M here, class, is the number of the vectors. That is its definition here. If you can go back here, your R of A is equal to M, V1, V2, Vm. So it's here, it's the number of the vectors here, if it's equivalent to that in your rank of A. Okay, next. Okay, now we have to define now a basis. By the way, in defining the basis class, we need that one. Definition of the linear independent and linearly dependent, and also the spanning set definition. We have this one. Your S there is a set of vectors in a vector space V. Then S is called a basis for V if your S spans V and S is linearly independent. Okay? If your S spans V and S is linearly independent. So we have here we have to satisfy these two parts for S to be called a basis. So the number of vectors in a basis S for V is called the dimension of vector space V. We denote it dim V. So the dimension class, again, it's the number of vectors. So here, for example, this S from V1 to Vn, the dimension of your V here is equal to N. Okay? Because that is the number of vectors there in that basis. So for example, this one, because we have the I, J, K. Your I is this, your S, is, your J is this, and K is this one. This is a standard basis for our three. Now, how many vectors we have here? Three. So the dimension of your V here is equal to 3. Okay? Your dim V is equal to 3 here. Now, this is your S. Plus, as you can see here, the numbers are elements. It looks like the numbers in your identity matrix, right? The 100, the 010, and then the 001. Because when you have that vectors class, when you multiply any element in the R3, for example, x1, x2, x3, okay, you can express it like this. You multiply x1 here, and then x2 here, and then x3 in this number. Okay, by the way, class, if this is the standard basis for R3, the standard basis for R2 is this point. This vectors. Wait, I will go back. For the R2 is this one. It will span. So is this linearly independent set? So we have there 1 0 0 1 in the matrix. If you get the determinant here, the determinant is not equal to 0. It's equal to 1. So if the determinant is 1, is it linearly independent? We go back to this one. We will check the determinant. Oh, it's here. The determinant is not 0. It is linearly independent. So it will satisfy the two definitions for basis. We have there spans V and linearly independent. Okay, so that is actually your standard basis for R2. Okay, this one is for the R3. So indeed, so for all x, as I told you, x1, x2, x3 element in R3, we can express that like this. We multiply x1 in your I, x2 in the j, and x3 in the k. And okay, that's it. It will span R3. And also, what he did here for linear independence, he just show that if you multiply their alpha, beta, and gamma, okay, and then equate that to 0, the number that we can get for alpha, beta, and gamma are all zeros. And we have this also as definition for linearly independent. Um, it is linearly independent if all the numbers there are zeros, right? This is what you call actually the lambdas, the lambda 1, lambda 2, lambda 3, and then they uses alpha, beta, gamma here. Okay, and that's it. So therefore, S is the basis for R3, and the dimension of R3 is equal to, again, just count the number of vectors. There's only 3, so the answer is 3. Next, another definition for the basis. S is a basis for a vector space V. Then every vector W element in V can be expressed in this form. W is equal to x1 v1, x2 v2, xn vn in exactly one way. So the scalars x1, x2, xn are called the coordinates of W relative to the basis S. We denote this WS is equal to x1, x2, xn, then T there, transpose. And that's it. This is your definition for the coordinates of W relative to the basis S. Okay, so find the coordinate vector. Actually, class, this one is the coordinate vector because it's not here, but it's um, containing the coordinates of W relative to the basis S. And this one, class, the WS is your coordinate vector. Okay? Of W, which is equal to 6, 5, 4, relative to the basis S, if this is the basis. So we have to find it. So to find it, we have to use this. Okay. W is equal to 654, and it's equal to, we multiply here with x1, then x2 in the second vector, and then x3 here in the third vector. And then you will say, like, can we use lambdas there, like lambda 1, lambda 2, lambda 3? Yeah, it's up to you. You can use that um, variable lambda. Okay, now next, you substitute, you multiply it here, class. So add the first component. So first component here is 6. Here the first component is x1. First component here is 2x2. And the first component here is x3. Okay, now for the second components, we have there 5 as the second component. And then the second component here is x1. Here it's x2. X3 here is 0. So only x1 plus x2 is equal to 5. Now next for the x3 third component, you have here 4. And then here the third component here is 0. So there is no x1 there. 3x2 and then 2 of x3. So 2x3 here is equal to 4. Now, if you are going to solve this, you have these values. Uh, 3, x3 is negative 1, x2 is 2, x1 is 3. So that is a system of linear equations, class. So you can solve this using the augmented matrix that you have, right? Yeah, they're 110, 213, 102, and then 654. Just get the numbers there. Then after that, make the side here, the left side, be like elements of your, or the entries should be look like the identity, and then the numbers here are the answers. Okay, so to do that, we use MATLAB, so it's easier for us to verify if that answer is correct. We have there A is equal to, just type the numbers there. We have 1, 2, 1, 6. You include the answer 6. Next we have 1, 1, 1, 0 for your x3, and then 5. And then next we have 0 for the x1, 3, 2, and then 4. Okay, that's the last one. So we have this augmented matrix. So what to do? So in using your MATLAB, just get the RREF, reduced row echelon form. of this. So this matrix 3 by 3 becomes the 100, 010, and 001. And the answers are here at the side. Okay, click enter. And we have this one. So x3, this is the column for x3. The answer is negative 1. The x2 is equal to 2. And then your x1 is equal to 3. So we are correct, right? Yes, 3 to negative 1. We have that. And that is now your coordinate vector of S. Then just arrange it. So 3 to negative 1 and then write T there. And that's it. This is now your coordinate vector. Next, we have this. In matrix form class, you have this one. You multiply it here with your coordinate vector and you can get the W. Okay, and we have that B, W, B is equal to W transpose. And then what to do, transfer the B there to the other side so we can use this. B inverse times the W. Okay, so again, we can use this one in solving your WB. This is WS, right? So what to do, get the, if this is S now, this is S inverse times the W T transpose, W transpose. So if you have this, okay, can we try this part here? Okay, your B, this are the numbers in your B, right? 1 to 1. Can we try this if this is really equal to your WB? Um, if your B is equal to that number. Okay, we'll try 1 to 1 and then 110. After that, 032. This is your B. So class, to get the inverse, you partner that with the I3. This is your I3. So we can write this here an A. Your B partner with I. Okay. Now to get the inverse, we have to get the RREF of A. Okay, so the contents of your inverse are this one. So that is now your B inverse. So we can label it another B here. This is now your B inverse, not the usual B. I'll just copy the numbers. Okay, we will not use that column class, that we can use the C there because the result is different. Just copy the numbers there. And this is now your B inverse. Now we multiply it with our W transpose. Our W transpose is equal to, can use capital W here. Okay. Our W there is this, 654. So we cannot use class a 1 by 3 matrix. Since this is 3 by 3 matrix, we have to multiply a 3 by 1. That is why it is a transpose. So is that 6, 5, negative 4? I forgot. 654. 654. So 6, you use now class a semicolon so that it will go down. So this is your W, 654. 3 by 3 times 3 by 1. And that's it. We multiply this. b times w. We should get class the 3 to negative 1. And we got that. 3 to negative 1. So therefore, um, you can use this formula also. Okay? That's it. You get the B inverse and then multiply the W transpose. You can get also the coordinate vector. Or you can use this is equal to 654. Then just get the value of your x1, x2, x3. Okay? Just solve this equation. And that's it. It's up to you any method you want to use in solving the linear equation. And next you have this one. It's 9:52. You can now have your 10-minute break. Okay? So we will go back at 10:02. Okay, it's time already. Hello, can you still hear me? Is it a yes? Okay, yes. Okay, by the way, the slides class are all available in your LMS already. You see it there, vector spaces. So we have this. If B is this one, E1, E2 to En, and your B prime is E1 prime, E2 prime to En prime, are two bases for a vector space V. So you can say here, class, that the basis class for a vector space is not unique. Okay? So suppose that W element in V, then we have this one. W is equal to the summation x k e k, k from 1 to n, or the W b here, the coordinate vector WB is equal to this x1 to xn transpose. And if you have this, W is equal to the summation of xi prime, ei prime, I from 1 to n, or the coordinate vector of W with respect to B prime is we have this. Okay. So how are the coordinate vectors, this one, WB and then the WB prime related? So suppose that there is a relation between B and B prime. So if this is your E I prime, which is equal to this summation SKI EK. Okay, so this one is if your I there is 1, so this becomes 1. This is 1, 1, S11, S21 to SN1 EN. Now for all, this is for all I from 1 to n. Okay, so if your I there is 2, so replace that numbers by 2. Then if that is n, the last one, and this becomes your i's here becomes n. So S1, S1n, S2n, and then SNN here, e to the en. Now, the matrix S class that they can form from this one, we have their S11. The S12 is located here in the first number in your E2 prime. Okay, so you get the numbers here in the first column. It looks like a column here. So in this line here, get that, and then you arrange it here in the first row of your S. Next, you have this second row, right? Because they are all S2 here. S21 up to S2n, then you arrange it here. Then the last, arrange it there. So this is your matrix. S is called the transition matrix from B prime to B. We denote it by S is equal to pass B, B prime. Okay? W is equal to that summation. X I prime E I prime. Then your X1 prime E1 prime. This is the summation now if you substitute there 1 first, then 2, and then the last is the n. Now, your E1 prime value is equal to that one because of this. This is your E1 prime and this is your En prime. You substitute it there. The red ones there, now the red ones here. Now after that, um, you multiply this by x1 prime, this one also x1 prime, and then this one x1 prime. Here x2 prime, here you distribute, and then here also xn prime, and then an xn prime here also. Now what to do next is you get the factors with the E1. Okay, for the E1, just get the first, it looks like the first number here So for your E1, it is S11 times S1 prime. So we have this first number plus the next E1 is located here in the first of your X2 prime. So you have it S12 times X2 prime. And your last E1 is located here. Can you see the cursor? You have their xn prime times the s1n. So here, s1n xn prime. That's for the E1. Next, follow until E2, and then last is your En. Now, as you can see here from W with the xi prime, we can express them with E1, E2, En. And that is actually now your xk. So this one, take this all of this to be x1. And then this values here, the black ones here, make that x2. And then this one, sn1, x1 prime until snn, xn prime, make this your xn. Okay, and we have that. So your x1, so your x1 here is equal to this with the x1 prime. So it's here. X2 prime, xn prime, x2 until xn. Now you have their x sub i's here and then equal to your s. Your set S here is your transition matrix times the x1 prime, x2 prime, xn prime. And this is actually your um, coordinate vector with respect to B. We have their WB. And this one is the set S. And then this one is the WB prime. Now, to solve the WB prime, you can just substitute transfer S here to the other side. So you have your S inverse of your WB. That is your WB prime. And we have this example. Consider the basis. B is equal to that one, and then B prime is that for R3, and your W is 8, negative 4, 6. um Number one, find the transition matrix S from B prime to B, and then find the coordinate vector W relative to the two bases B and then B prime. So for the part two class, we're going to find the WB there and then the WB prime. Here, finding transition matrix S. Now, um, we form this one. E1, E2, E3, they uses this variable E here for the what do you call this one here? Vectors in part B, okay, which we use there because we use their E's, right? If you go back here, your B is E1, E2, En. That is the label. And then your B prime vectors are E1 prime, E2 prime, En prime, so that we have the same labeling. So this one is E1, E2, E3. And then for the B prime basis, you have there E1 prime, E2 prime, E3 prime. Now, for this one, E1 prime is equal to this. S11 E1, S21 E2, S31 E3. We just follow this format here for your E1 prime. This one. So S11 E1, S21 E2. So the next is S31 E3. Correct? And then the last one is E3 prime. You have there S13 E1 plus S23 E2 plus S33 there, the last one, right? And E3. And that's it. You have this. Yes, this one. Now, what to do next? For E1, um, it says that E1 prime, this one, you have their S11 times your E1. Your E1 is 210. Your E2 is 103. And then S31 times 001 it's equal to your E1 prime. Your E1 prime is 101. This is the E1 prime. Okay, what to do? Get the first coordinate here. So that's 2s11. The first coordinate here is s21. First coordinate here is 0. Then first coordinate there is 1. Okay. Again, combine all the first coordinate. Next, second coordinate. S11 here. Because there's only 1 here in the second coordinate. 0 in the second coordinate here. So there is no S31 here. 0 also here. So there is no S31 here. Is equal to 0. Okay, this is the second coordinate. Now next, the third coordinate here, we have S11 times 0, so 0 here. The third coordinate is 3 S21 plus the third coordinate here is 1 times this is S31. It's equal to the third coordinate, which is 1. Now class, you solve the values. Okay, we have um, the easier way to solve is the row 1, row 2. For row 2, it has a value already. Your S11 is 0. So here it's 0. Now you substitute it here on the first equation. If this is 0 here, um, your S21 is 1. Correct? Because this is 0. S11 is 0. Multiply it by 2 is 0. So S21 is equal to 1 directly. We have there 1. Now if your S21 is 1, substitute it here in the third row. 1 here. So 3 times 1, it's 3. Transfer the 3 to the other side, it becomes minus 3 there. So 1 minus 3, your S31 is negative 2. And then after that one class, since as you can see there, there are 1, 1, 1 in the second number. So it means that they are in the first column, correct? So in your S there, arrange that numbers in the first column. You have there 0, 1, negative 2, because we are going to get the S, right? The transition matrix S. And then your S is this arrangement here. So they're all one there at the second number. So they are arranged in the first column. That is why your answers here must be in the first column of your S. Now, in matrix form, so transform this to matrix, you have this. And then we multiply the S11, S21, and S31, and you can get the 101 there. Okay? Now, if you want to get the value of your S11, S21, S31 here, what to do? You form the augmented matrix, right? So 2, 1, 0, 1, 1, 0, 0, 0, through 0, 3, 1, 1. Then after that class, form this 3 by 3 matrix, transform this into an identity matrix so that you can get their values. Okay, so as you can see here, it's 2 in the starting matrix. You can switch that here with the row 2. So you transfer row 2 to row 1 so that 1 is the number here, right? So it's 100 on top now, and then 210 second row. You do it like that, and then you make the lower numbers their zeros. The next, you had to pick a row such that the second number here in your second row, second column number, it should be 1 here also, and then make the zeros here, the top, and then the lower number here, and then next make this number here 1, and the numbers there at the side are now the values of your S11, S21, and S31. So to check this using our MATLAB, okay, we type it there. And that's very easy. All you have to do is to get the RREF of that matrix. So if we have there matrix A, we label it A, 2, 1, 0. The answer is 1 there. So this we include the answer 1000, and then last we have 0311, and that is your A. And then compute the RREF of A there, and you can get this values. We have there 0, 1, -2. Are we correct? And we are correct. It's there 0, 1, -2. That's the value of your S11, S21, S31 by solving this using your MATLAB. Okay, next, A2 prime. For the A2 prime, just copy this one equation that you had. So we have there. And as you can see, they are all column 2. Okay? So S12, S. So look at class. The number is easy to memorize, right? You have there 2. So S12, because they have the same number 2 here in the second number. So 1, 2, 3, arrange it like that, and then 2, 2, 2. And then for your E, we have there 1, 2, 3. So S12 times your E1, E1 is this, S22 is 103, your S32 is 001, and you have this 0, 1, -2 as the answer. Now you get the first coordinates, so we have this equals 0. The second coordinate now, we have there S12 is equal to 1. And then the third coordinates here, we have 0 for the S12, 3 times S22, 1 times S32 is equal to -2. Now, the easy number that we can solve is in the second row. So S12 is 1 directly. So we have 1. Replace this with 1 here, so it becomes 2. Transfer this to the other side, so 0 minus 2, that is your value of your S22. S22 is -2. If you substitute here S22 with -2 times 3, it's -6. Transfer -6 to the other side, it becomes +6. So -2 plus 6 is equal to 4, which is your value for your S32. And in matrix form, we have that. Now we will type it with our MATLAB to check if this is correct. 1, -2, 4. We just replace that number there with 0, 1, -2 because they're the same. So go to MATLAB, 0, 1, -2. Okay, here. I just copy that. This with 0. This is 1. Now, it's -2. Okay. So we have that matrix. Then after that, we reduced it, reduced row echelon form of A. So we really get the value, right? It's 1, -2, 4 in the last here. So that's it. 1, -2, 1. We have the E3 prime. Okay. That is the formula. You substitute now your E1, E2, E3. And that's equal to 013. Your 013 here is your E3 prime. Okay. And that's it. Okay, so row 1, your S13 is 1, and then substitute it here 1, transfer it to the other side, it becomes -2. And then if this is -2, here it's -6, transfer to the other side, it becomes +6. So 3 plus 6, your S33 is 9. And this is the matrix form. And if we solve that, it's 013. Go to your MATLAB, change the last numbers here by 013. It's only this, right? 013. Is it correct? Yeah, 013. Enter 013 there. Then get the RREF of your A. And this is the answer 1, -2, 9. And we are correct. And this one plus you arrange this in the third column. The 1, -2, 9. The second column is 1, -2, 4. Okay, the first column is 0, 1, -2. And you have this transition matrix now. 0, 1, negative 2, 1, negative 2, 4, and 1, negative 2, 9. Okay, other way classifying, we have this. If this is the matrix, B is equal to times the S is equal to the numbers here are from your B prime. Okay? So transfer this to the other side. You have to take the inverse of that matrix first before you multiply it here. So to solve this using our MATLAB, we have to get the inverse first of our B. Okay, so go here. Your matrix B there is equal to um 2, 1, 0 and 1, 0, 0. Then last we have 0, 3, 1. Okay, that is your matrix B. Now partner that with we label it with A now. Partner that with I so that we can write it like the I there is at the other side. So it's here. Now get the inverse. So to get the inverse class, what to do, you make this the first three columns be equal to your I3, and the numbers here at the other side is now your inverse of your B. Okay, so to get that, we use another variable C there, then RREF of your A. This is now your B inverse class. So your B inverse is this. So when we type it, I will just use another B, but this one now is your B inverse. I'll just get the numbers here. 0, 1, 0, 1, negative 2, 0, and then this one, copy, and okay, this is now your B inverse. We multiply it with our B prime. The B prime is this, right? 1, 0, 0, 0, 1, 1, and 1, negative 2, 3. So B prime, we can just use V, okay? Because we cannot use B prime here. We have there 1, 0, 0, semicolon, 0, 1, 1. And then last we have 1, negative 2, 3. So class, this makes sense because this is 3 by 3 matrix times 3 by 3. The result must be also a 3 by 3 matrix. That is why your S here is also 3 by 3. So if you multiply them now, the B, okay, your S now is equal to your B times V. Okay, again, the entries for your B here is your B inverse. And then this one, the entry of your V here, V is your B prime. So let's try if this is really correct. And yes, we really get the correct answer. We have there 0, 1, negative 2, 1, negative 2, 4, and 1, negative 2, 9. And we got the S also. So this is the other way class of finding your S transition matrix. You can use this. Okay? Just multiply the inverse of your B to your B prime. And you're done. Now, if the question there class changes, like what is the transition matrix S from B to B prime? If you say they're from B to B prime class, what are you going to do is switch this. First is you multiply the B prime inverse to your B. Okay? Because it's here from B prime to B. So what if from B to B prime? So from B to B prime class, so it means that your B prime must have the inverse, then multiply it with the B. Okay? Okay, please do not be confused on that one because yes, there is another question. If it's from B to B prime, if you switch the B here and B prime, you switch here also. Okay, so as you can see there, from the from part, you will not get the inverse of that. This is your B prime here, right? The entrance of your B prime to B. So when you have there to B, the B there must you have to get the inverse of this. Okay? Okay, so that's the hint there. So from so what is the matrix here? Do not multiply it or do not get the inverse. Okay? You have to write it at the right side. So the left side here is contain the inverse. Now, if it's here, this is B, so 2B. So the matrix next to the word 2 there, you have to multiply, you have to get the inverse there. Okay? And that's it. That's the hint. Okay, next, we have this one, um, E1 to En. Multiply with that is equal to your E1 EI to En. So this one class is from your uh, basis B, and this one now class is from your W of B. So it's here B W B. So the your coordinate vector, okay, W, and here is your um, W B prime. This is for the WB prime, right? Yes. Ah, wait. This is for a B prime. Okay. So what we're going to use here for your WB class, the coordinate vector B, you can use this equation. Okay, we have S times W of your B prime. Oh, so if you have there an S already, transition matrix, and you have another coordinate vector with your B prime, you can get the coordinate vector W of your B there. Just multiply them. Okay? And that's it. Next, find the coordinate vectors of W relative to the two bases B and B prime. So first, what are we going to do is to get the W is equal to lambda 1, multiply that with E1, lambda 2 E2 plus lambda 3 E3. Okay, now you substitute there. Lambda 1, oh, we use here lambda 1. So again, it's really okay. You can use any variable you want here, like a sub 1, a sub 2, a sub 3, it's up to you. So first, lambda 1 times E1. E1 is 210. Lambda 2 times E2. The given E2 there is 103. Then lambda 3 times 001. It's equal to your W. W is 8 negative 4 6. Okay. So we have there 2 times the lambda 1 here plus 1 times lambda 2. This is the first coordinates class. 0 in the third coordinate. So there is the first coordinate here in your third vector. So it's 0 here is equal to 8 here, the first coordinate also. Now for the second coordinates, you have there lambda 1, 0, 0. So there are no here. And negative 4. So as you can see, class lambda 1 is easy to solve. It's negative 4 already. Next for the third, 0 in your lambda 1, 3 times lambda 2, 1 times lambda 3 here is equal to 6. Now your lambda 1 is negative 4. Now substitute it here in your first row. So if this is negative 4 here, 2 times negative 4 is negative 8. Transfer the negative 8 to the other side, it becomes plus 8. So lambda 2 is 8 plus 8, which is equal to 16. Now, if your lambda 2 here is 16 times 3 here, it's 48. Transfer to the other side, it becomes minus 48. So your lambda 3 now is 6 minus 48. The answer is negative 42. And this is now your WB. Okay, so that's easy to do. What to do, just solve it. uh the lambdas there's, if you multiply it with your basis b there, and it's equal to that, 8 negative 4 6, and you have this one. Now how to get the coordinate vector w with respect now to your b prime. So you use here e1 prime here, e2 prime, e3 prime, correct? And it's equal to your w again. And now class, you can solve a value there for your lambda 1, lambda 2, lambda 3 again. But there's another formula that we can use. Since we have this, if your WB is equal to S times WB prime. So to get the WB prime class, just transfer the S there to the other side, and that is S inverse, correct? And that's it. The WB prime is equal to S inverse times your WB. And now question, what is your S inverse? Okay, can we double check this? Mhm. Now you have your W. Did we solve the S inverse already? Not yet. Not yet. This is only S. Okay. We will take the picture of our S again here. Okay. So first we get our S inverse. So class, again, for this one, how to get your WB prime, you can use this one, and you can use also this. Um, Again, what to do there, W is equal to lambda 1 E1 prime. Just replace the E1 there by the E1 prime. This one E2 prime, and then E3 prime, and then solve the lambdas. The lambdas that you can solve there is your WB prime. Okay? It's your just arrange it like this, negative 4, 16, negative 42. So this is the other way of solving it, because you have their WB already. You get the S inverse. Okay, for in your MATLAB, to get the S inverse. This is your S, right? No partner that with I. We can use I there because I declared that already as an I3. So you have that. Next, C is equal to RREF of B. And this is now class the coordinates of your S inverse. Okay, so I'll just label that with S again. But this is for the S inverse, okay? Just copy the numbers here. Again, that is S inverse, that's because it's here. This is identity here at the other side, right? That one, too many space, but it's okay. This, and then the last one is this. Enter. Okay, this is now your S inverse. Now we multiply it with our WB. I label it with W. The W, the WB there is negative 4, 16, negative 42. Negative 4, 16, negative 42. And that's it. We multiply it here with your S. So S times W. Again, class, this is for your S inverse, and this is for your WB. When you multiply it, it's the WB prime. And we are correct. 8, negative 2, negative 2, which is here. 8, negative 2, negative 2. Okay, so that's it. It's the other way around of solving your WB prime. Again, the other way of solving that is you substitute it here, e1 prime, e2 prime, e3 prime, and then solve the lambdas. You should solve there 8, -2, -2 also. And that's the same process. And that's the end of our discussion for the midterm. Now we are ready for review. So for the review class, I'll just give you the questions and you will answer it. I will give you like 5 minutes in each question. Okay? You have there midterm review, classroom rules. So question number one. Given two matrices A element in the set of matrices 2 by 4. So it means class that your A here is a 2 by 4 matrix and B is element in M 5 by 5. So your B there is a 5 by 5 matrix. Let X and Y satisfy this. Your Y is equal to A X times B. Then what is the size of your X? So where is the set X here? The matrix X here be an element. Again, we have um, the method for multiplying matrices, right? You cannot multiply if the number is not the same with the number of the columns here in the first matrix. It should be the same with the number of the rows there in your next matrix. Okay, so I will give you 5 minutes to do this, and this is very, wait, not 5 minutes. 1 minute is enough here. This is very easy. So after the time class, if you are done already, please you choose your answer and type it there in the chat box. Okay? Here class, you can answer it like seconds only. X there is between A and B. But for the questions here, I didn't have the slides for the answers. Only questions are here in our review. So are you done answering? Can I see it? Oh, oh my God, only one is answering. Where are the others? Nah. Class, that is very easy. What's your answer? Please type it now. I'll give you 5 seconds. Five, four, three, two, one. So only three? What's happening with the others? Are you listening in our class? Maybe you are not there. So we only have four. So the first one who answered it is Chung Hoon Lambao. Congratulations. That is the correct answer. Letter B. It should be B class because this is 2 by 4. Your A is 2 by 4. Your B is 5 by 5. So your X there must be 4 by 5. Correct? So that you can multiply it in your A there and the B. So it should be 4 by 5. And that's it. Your answer must be letter B. See, that's very easy. Next question, number two. Rank of the matrix. Again, how to get the rank? We make this one here, so it's one already. Next, make this 0, 0. Then make this one here, 0, 0 are here. Then make this one 1, 1. one here, the next this number, the the main diagonals there, because the entries of the main diagonals there, you should make it one, and the rest are zeros. No way to make zeros there at the top part. Okay, only here. You make this zero, zero, and then this three here, make this zero. If you can do that, then the rank is four. Okay, that's it. Your timer starts now, 5 minutes. If you are done, class, then it's okay. Maybe 4 minutes for this. I guess 5 minutes is too long. Or three. 3 minutes only. Continue. So next meeting class, I can still meet you, and then we will do review of the midterm questions. The questions here is from the 2023. So we also review questions from the previous exams. So I don't have a copy class of the real exam, but what I am instructed to just review the previous questions of the previous exams because they are very related to the questions in your midterm also. Do you have an answer now? Okay, write your letters there, class, now if you have that answer already. Is it one, two, three, four? None of the others. Because the none of the others class should not be an option because you only have four rows here. So the rank is the possible rank should be only one, two, three, four. In the test, if you answer none of the others, and then I will say, "Oh my God, what's happening to you? Why you answered none of the others?" There's only four rows there. So four is the maximum for the rank. Minimum is one, and it will never be zero for the rank. Okay, and it will never be five. Again, here, if you encounter this problem again, then none of the others is really not an option. So do not choose that. Okay? So it's easier for us to solve the rank if we type it in the MATLAB. Okay? So if you have there, um, 1, 2, 0, 2. Next we have 2, negative 1, negative 1, negative 4. Please type your answers there, class, already. 1, negative 4, 1. And last, we have 1, negative 1, 3, 4. And that's it. And then after that, just get the RREF of your A. And nah, it's too much. It's too much R. Yeah, RREF only of A. And you can form this. So what does it mean? You make all the main diagonals be equal to 1. Therefore, the rank there is 4. And the answer must be... Wait, where is that? The answer must be E, 4. Who answered E there? Oh, so the first one who answered it, it's Kwan Tran Nguk Min. Congratulations. Okay. Next we have again class. The rank is the number of leading ones, right? So it's four there. Next, last question number three. Maybe we can end the last question number three. Okay, this is very easy class. If this is your matrix with determinant 7 already, we solved the determinant. So determine the determinant of 2 times a cube. Your timer starts now. 2 minutes is enough here. Or 1 minute. That's very easy. 1 minute, yeah. Now, if you remember, your 2 there must be raised to the order of the n. This is a 3 by 3 matrix, so your 2 must be raised to 3. And then your determinant of a here, that is 3 there. So determinant of a times determinant of a times determinant of a. And your determinant is 7. Hmm. So what is the answer? You should have an answer now. Again, it's 2 cubed times determinant of a times determinant of a times determinant of a. Again, why it's 2 cubed? Because this is a 3 by 3 matrix. So if it's 4 by 4, it's 2 to the power of 4. It's not related with a cube here. Okay? It's a cube. And what's your answer? C? Only one? My God, what's happening to you guys? The determinant is given there already. It's 7. So that's 2 cubed times 7 times 7 times 7. Correct? And the answer is letter C, 2744. So only one got the correct answer. Oh my God. That's very easy class. 2 cube is 8. So times 7 times 7 times 7 times 7 divide 3 times, right? So it's actually equal to the determinant of a cube. And determinant of a there is 7, so 7 cube. And your 2 there is raised to cube also. So 2 cube times 7 cube, it's 2744. And that ends with our class today. We will review more questions next meeting. So, by the way, for next meeting class, you are not required to go there inside the classroom. But the chairman said that I can still meet you online. So we still have a class, online class only. So you have to use your own laptop there if you have, okay? Or your cell phones. You can install their Gmeet. And then please class, you use your official HCMUT email so that you can enter directly, okay? Goodbye, everyone. Thank you for coming. See you next meeting. Bye.